Hello everyone, welcome to lecture 21 in physical organic chemistry, in which we are studying the topic pericyclic reactions. In our last class we had seen the introduction to pericyclic reactions. We had formulated rules for determining the permissibility of variety of pericyclic reactions. Moving forward, today we will discuss the theory behind electrocyclic ring closing and ring opening reactions. Like I mentioned previously also, most of the material that I have sourced for this particular lecture and for the previous lectures too comes from Professor Shankaraman's book, Pericyclic Reactions, a textbook, and his lecture notes. Let's now first define the generalized orbital symmetry rules before we move on to electrocyclizations. Very important terms that we need to remember are the suprafacial and anterofacial cyclizations or reactions. Okay, these terms describe the topology of the interaction of a given system in a pericyclic transition state. Okay, and they are defined with the figure that is shown below, where the lines appear as loops or arcs. Okay, and it indicates where the interactions occur on the orbitals. These lines will define a geometry for interaction of the orbitals as shown with other orbitals. Okay, so if the two orbitals in the similar phases are reacting from the upper side, then these are suprafacial. If they are reacting with opposite ends, then these are anterofacial. This is for a pi system. Okay, for a sigma system, if the two lobes are opening up from the same side and they are reacting with the same phase, then it is suprafacial. If they are reacting from the opposite ends with the same phase, then it is also suprafacial. If it is suprafacial with the antibonding orbital, then also, okay, then also it is suprafacial. It will be anterofacial when opposite lobes will react. Same is true for a sigma bond with an S system involved, like you see here. When the same ends are reacting, then it is suprafacial. The opposite ones are reacting, then it is anterofacial. For the omega systems that are the lone pairs, if one of the lobes is reacting, then it is suprafacial. If opposite ends are reacting, then it is anterofacial. Like I mentioned, for the pi systems and the lone pairs, the distinction is rather simple. The suprafacial interactions will involve the same face of the system, whereas the anterofacial interactions will involve the opposite faces. For sigma bonds, it is little difficult and it's not that obvious, but it is the same as other systems. With the suprafacial interactions, the loops are drawn to either the inner lobes or the outer lobes, while with the anterofacial interaction, one loop will be to an inner lobe, whereas the other loop will be to an outer lobe, as you can see in this particular figure. Now, the suprafacial interaction at a sigma bond involving two sp3 hybridized carbons can lead to double inversion or double retention of stereochemistry. This is very important. On the other hand, an anterofacial process will lead to inversion at one center and retention at other center. We will see what this means, especially when we see the electrocyclizations and the sigmatropic shifts. But this is very important and needs to be kept in mind. Now with these definitions, we can describe a new symbolism to describe the pericyclic processes. The components of a reaction are actually the parts of a molecule. They can be separate bonds or conjugated bonds that undergo a change during a pericyclic reaction. Okay. So what does this mean? This means that the components which are going to react are going to be a part of a molecule. Okay. These could be either separate bonds or they could be conjugated bonds. We then assign an electron count to that particular component, and we assign a suprafacial or anterofacial descriptor, and we identify if the component involves either a pi bond or a sigma bond. For example, if the component of a transition state, or it could be the entire transition state itself, contributes 4 electrons in the pericyclic array, and the electrons are contained in a pi system, and the interaction of the pi system is suprafacial, then the designation for this particular component will be pi 4s. Okay, so 4 electrons, all of them are pi, and they are interacting in a suprafacial manner. So the designation for that particular component will be pi 4s. Okay. Alternatively, if you can have a 2 electron sigma system, okay, for a sigma bond which has an anterofacial interaction, then you would have a designation of this kind, sigma 2a, where 2 electrons are contained in that sigma bond. It is a sigma bond and it is interacting anterofacially. So this particular designation for that component would be sigma 2a. The lone pairs, as I had mentioned earlier, are denoted by omega. Okay. Now let's see this particular transformations. This 2 plus 2 cycloaddition. Okay. This is a pi system. Both of these are pi system. This is 2 pi system. This is 2 pi system. And these are interacting in a supra-supra manner. In this case, this is a 2 pi system, and this case, this is a 4 pi system, and these are interacting in again a supra manner. What we need to keep in mind is that the number of electrons involved in the process, okay, it does not matter how many orbitals are being involved in this particular process. For example, the allyl system. The allyl system, you see here, is now a pi 4 system when it is anionic. Whereas when it is cationic, it is a pi 2 system. Okay. Although the number of orbitals involved in both the cases is 3. Okay. But it is still in one case the pi 4 system and in the other case the pi 2 system. So it is the electron count that matters and not the number of orbitals. So we have now this descriptor in hand. Let us now look at the generalized orbital symmetry rule that is given by Woodward and Hoffman. Now there is a definite binary nature to the theory. Okay. For example, 2 plus 2 cycloadditions are forbidden when it is supra-supra, whereas 4 plus 2 is allowed when it is supra-supra. In the same series, if you continue, 6 plus 2 is forbidden and 8 plus 2 is allowed in the ground state. We will also see this kind of descriptions and similar patterns when we see the electrocyclization reactions and symmetropic shifts. At this moment, we are seeing these descriptors for cycloadditions. Now, based on these, Woodward and Hoffman had proposed a rule, a basic fundamental rule for all pericyclic reactions, which says that a pericyclic reaction is allowed if the number of 4q plus 2 suprafacial components plus 4r anterofacial components is odd, where both q and r are integers. That means for the suprafacial component, 2, 6, 10, 14 electrons are considered, whereas for the anterofacial component, 0 when R is 0, 4, 8, 12 electron components are considered. So, if this is odd, the pericyclic reaction will be permitted. If the number is even, the reaction is forbidden, depending on whether it is thermal or photochemical. Let's now look at the cycloaddition reactions that we had seen earlier. Let us see whether we can implement this method of the generalized orbital symmetry rule. We are saying that the first reaction is a pi2s reaction. Both are suprafacial, involve 2 electrons each, and they both fit in the formula 4q plus 2. That is a suprafacial where q is equal to 0. Hence, there are two components in this reaction that conform to the generalized orbital symmetry rule. Now, 2 is an even number, therefore the reaction is forbidden in the ground state. That means thermally. Let's look at the 4 plus 2 cycloaddition. In the 4 plus 2 cycloaddition, it is now a pi 4s plus a pi 2s reaction, in which only the pi 2s component fits into the 4q plus 2, where q is equal to 0. Okay. Now 1, since we have only one component, 1 is an odd number. Therefore, this reaction is allowed in the ground state configuration, that is the thermal state. Okay. So in a thermal condition, this reaction, the pi 4s plus pi 2s, will be an allowed reaction. This rule is very important. It's very powerful, especially when there are several components in a pericyclic reaction. However, with several components, it's sometimes difficult to identify appropriate HOMOs and LUMOs for a frontier molecular orbital analysis. And it is rather difficult sometimes to write an orbital or a state correlation diagram. So in such cases, the aromatic transition state theory or the generalized orbital symmetry rule, okay, these are the easiest approaches for analyzing whether the reaction will be permitted or forbidden. Okay, you can use a variety of these methods to analyze a pericyclic reaction. It is up to you what you are most comfortable with. Now there is a little bit of a catch here. When we say that a reaction is forbidden, what we really mean is that there is a very large barrier on the reaction path that results from unfavorable orbital properties of the system, which we call an electronic barrier. We can arrive at this conclusions based on orbital correlations or state correlations or some other models that we want to use, but essentially this basic concept remains the same. The electronic structure of the system is not especially favorable for the reaction to proceed in the geometry considered. Okay, what do we mean by this electronic barrier? The reaction actually is not really forbidden. It's just that if the reaction has to occur, it has to overcome this electronic barrier in addition to any other barriers that are present in the system. For example, steric effects. Okay. Alternatively, the reaction can proceed along a different geometry with a transition state which has a completely different structure from the one that we use in our orbital analysis. Or it is possible that the same transformation can give the product in a reaction that occurs stepwise and not in a pericyclic fashion. Therefore, all forbidden pericyclic reactions are allowed in alternative geometry. Okay. Although the allowed path may be unfavorable due to some kind of a strain or very low orbital overlap. So the bond formation may not be efficient. In the same sense, a reaction that is allowed is simply one that does not have or possesses a low electronic barrier. That does not indicate that the reaction will be favorable. Okay, it doesn't mean that you set up the reaction and it will work. The steric interactions or other factors could make the reaction really quite slow. What we know is that there is no additional barrier due to electronic factors that contributes to the overall activation energy. For example, the two cycloadditions that we saw on the previous slides, the 2 plus 2 cycloaddition is forbidden thermally. But nonetheless, you can still dimerize olefins to make cyclobutanes. It's just that the reaction will not be concerted. Now it will involve a biradical intermediate. So you can still achieve the same result, but not via pericyclic pathway. Similarly, if you take the reaction of ethylene with butadiene, then on paper, the 4 plus 2 cycloaddition is thermally allowed. However, in practice, the reaction will require very high temperature and pressure. That means the activation barrier for this transformation is rather high. The reaction does occur at high temperature and pressure by a concerted path, but this indicates that this is a pericyclic reaction. However, the activation barrier for the same reaction is rather high. Let's now begin our discussion on electrocyclic reactions. An electrocyclic reaction is essentially defined as the reaction of an acyclic conjugated polyene system in which the terminal carbon atoms interact to form a sigma bond and thus form a cyclic system. During this course of reaction, the ring closure step, the pi system is then reorganized in a concerted manner. For the sake of convenience, the reorganization of the electrons can be represented by curved arrows, okay, as it is shown here. Now the curved arrows can flow either in a clockwise or an anti-clockwise direction, as it is shown here. Okay. Usually, electrocyclic reactions are generally, reversible. So it is possible to go from a cyclic system to an acyclic system by breaking of the sigma bond and the reorganization of the pi bonds to give you an acyclic conjugated polyene. As you can see in these reactions, the backward transformation in both the cases. Now, one important factor that we have to take into consideration that we have drawn all these polyenes in the S-cis configuration. Okay, it's not necessary that all of these will exist in the S-cis configuration. Okay, or the conformation. So these are deliberately drawn this way so that the carbons at the terminal positions of the polyene system are able to approach each other for bond formation. Okay. In the S trans conformation, unfortunately, this is not possible because the distance between the terminal carbons will be too high for bond formation. However, one has to take into consideration that this change in conformation from S trans to S cis will also involve energy. Okay, and the orbital diagram that you write, the energies for the S cis and the S trans will be slightly different. Okay, so one has to take this into considerations. Now, the electrocyclic reactions can be classified according to the number of electrons that are involved. Okay, for example, you can see here the butadiene, all 4 electrons are involved in the reverse reaction. There are 2 electrons that are in the pi system and 2 electrons that are in the sigma system. Therefore, the electrocyclization of butadiene to cyclobutene and the reverse reaction will involve a total of 4 electrons, and therefore it is a 4n electron system where n is equal to 1. Similarly, if we analyze the electrocyclization of hexatriene and cyclohexadiene, then the forward and the reverse reaction involve 6 electrons. The forward reaction involves 6 pi electrons, whereas the reverse reaction involves 4 pi electrons and 2 sigma electrons. Therefore, it's a 6 electron system, making it a 4n plus 2 electron system where n is equal to 1. Now, before we go on to what is allowed and what is forbidden, we first need to look at some new terminology. So this is how a bond is going to either form or break. That means we are going to move in orbitals either in a conrotatory or a disrotatory fashion. Okay. So if the lobes are going to move in separate directions in opposite senses, then it will be a disrotatory out system. If they are going to move in opposite directions towards each other, it's a disrotatory in system. And similarly here, as you can see, the same system is depicted here with lobes in this particular case, whereas in the conrotatory it will move in one single direction. Both the lobes are going to move in one single direction, either in the right direction or the left direction. It could go in the clockwise direction or in the counterclockwise direction. For the sigma systems also, same terminology is going to be used. If they are going to move out in uh, different directions or opposite senses, then this bond breaking will be a disrotatory process. Whereas in this case, if you are seeing here, again, we are moving these in opposite senses and we are having the bond breaking in a disrotatory manner. For a sigma system, if the bond is breaking and the lobes are going out in similar senses, okay, either in the clockwise or counterclockwise direction, then it will be a conrotatory process. Let's now consider the following transformation. The transformation for either cis or trans 3,4 dimethyl cyclobutene. Now, during the breaking of the sigma bond, the carbon atoms that are C3 and C4 that are C3 or C4 can either twist in the same direction or in the opposite direction. Now the stereochemistry of the product, okay, it will depend on the mode of twisting of C1 and C4 and C2 and C3 sigma bonds. Okay, that means these particular bonds. Okay, if these two sigma bonds are twisted in the same direction, then the stereochemistry of the resulting product is Ze. It will be Ze hexa 2,4 diene. Okay. Now this mode of ring opening will be obviously it is a conrotatory ring opening. On the other hand, if the sigma bonds are twisted in the opposite direction, then the stereochemistry of the resulting product will be either EE or it will be ZZ or ZZ. Okay, depending on whether the substituents are twisted inward or outward. Now, there are other factors involved in this which will decide whether this is inward or outward. We will come to this a little while later when we consider specific examples and what steric factors are involved in these. So, obviously, this is a conrotatory type of ring opening in both these cases. So, in this particular case, we are seeing the conrotatory opening, and in this case, we are seeing the disrotatory opening. Now, the same process can take place during ring closure as well. Okay, so the Ze, which is this particular substrate, will end up giving you the cis product on conrotatory ring closure, whereas the EE and ZZ isomers, okay, the EE and the ZZ isomers on conrotatory ring closure will give us the trans product, okay, as you can see here. Similarly, the ZE, okay, on disrotatory ring closure will give us the trans product, whereas the EE and the ZZ will give us cis products on disrotatory ring closures. Okay. Let's now analyze the electrocyclizations using the frontier orbital method of analysis. Now, for this, we have to first identify the molecular system undergoing the electrocyclic reaction. So we classify this as either a 4n electron or a 4n plus 2 electron system. Then we choose the HOMO of the system and analyze for two modes of reaction, that is the conrotatory mode or the disrotatory mode. Based on whether the interaction of the orbital on the terminal carbon atoms corresponds to bonding or antibonding interaction, the permissibility of the reaction is predicted. Let's now consider the classical case of the ring closure of butadiene to cyclobutene. We have seen earlier this belongs to the 4n electron system, and we know that the HOMO for butadiene is the pi2. In the conrotation or the conrotatory mode of cyclization, it leads to a bonding interaction in the transition state at the terminal carbon atoms in the HOMO of the ground state. Okay, this is very important. And therefore, since this is a bonding interaction, this conrotatory ring closure is thermally allowed. That means it is allowed in the electronic ground state. Whereas the disrotation, now you see here we are moving this in this particular direction and we are moving this in the opposite sense. So what's happening? That this particular lobe is now going to interact with this particular lobe. Therefore, there is going to be now an anti-bonding interaction in the transition state. Therefore, the disrotatory mode of ring closure for a 4n system will be thermally disallowed. So in general, for a 4n electron system, the conrotatory mode of ring closure and ring opening is thermally allowed, whereas the disrotatory mode is thermally disallowed. Let's now consider the electrocyclic ring closure of hexatriene to cyclohexadiene. This now belongs to the 4n plus 2 electron system, and we know that the HOMO is the pi 3 molecular orbital. And obviously, since this is pi 3, so minus 1, that means it will have two nodes. So let's see whether we have drawn this correctly. So there's a node here and there's a node here, and both are symmetrically placed. So we have drawn the correct molecular orbital. All right, let's now try to see what happens when we do a disrotation. That means we are moving this orbital inwards, we are moving this orbital inwards, and there is a bonding interaction in the transition state. Therefore, in the ground state electronic configuration, the disrotatory mode of cyclization leads to a bonding interaction at the terminal carbon atoms in the HOMO. Okay, and therefore, obviously, it will be thermally allowed. Let's look at the conrotation mode. In the conrotation mode, we are going to move the orbitals in the same sense. Therefore, what is going to happen is that this particular orbital is now going to react with this particular orbital. So, we are going to have now an anti-bonding interaction in the transition state. So, this orbital is going to react with this orbital, giving you an anti-bonding interaction. Therefore, it will be thermally disallowed. In general, for a 4n plus 2 electron system, the disrotatory mode of ring closure and the ring opening is thermally allowed, whereas in the conrotatory mode, it is thermally disallowed. Okay. Now, if we consider the excited states of both butadiene and hexatriene, that means in a photochemical conditions. So what happens in the photochemical conditions? We excite one electron to the higher orbital, to the antibonding orbital. Therefore, it becomes a singly occupied molecular orbital and the HOMO for that particular system. So, in the case of butadiene, the HOMO for that system now becomes the pi 3 molecular orbital, whereas for the hexatriene, it becomes the pi 4 molecular orbital. Let's see now in the excited state, the conrotatory mode of ring closure and ring opening for butadiene. What happens here now? In the excited state for the conrotation, we are now seeing that there is an anti-bonding interaction. Whereas for the disrotatory mode, this is now leading to a bonding interaction. So what can we conclude? In the photochemical conditions, the disrotatory mode of cyclization for butadiene is now permitted, whereas the conrotatory mode of cyclization in photochemical conditions is forbidden. Whereas for the hexatriene case, now this is a 4n plus 2 electron system, and your pi 4 is now your HOMO. In such a case, let us see what happens when conrotatory mode is carried out. In the conrotatory mode, you are now having a bonding interaction in the transition state between the terminal carbon atoms and the lobes. Therefore, this conrotation and the mode of cyclization is allowed under photochemical conditions. Whereas in the disrotatory mode, you are now having an anti-bonding interaction between these orbitals. Therefore, it will be photochemically forbidden. It is usual for a system to be permitted in thermal conditions, whereas the opposite would be permitted under photochemical conditions. Let's now see some orbital symmetry correlation methods for electrocyclic reactions. So, in this method, we first identify the symmetry element that is maintained throughout the reaction in either the conrotatory mode or the disrotatory mode of action. Using that symmetry element, then the molecular orbitals are classified either as symmetric or antisymmetric. Once the symmetry properties of the molecular orbitals of the starting material and the product are identified, then it becomes easy to correlate and predict whether a process will occur in the ground state or excited state. Let's now consider the same butadiene type of system. Okay. Now it becomes very obvious that in the conrotatory mode, it is the C2 axis symmetry that is present all through the reaction. Okay, you can see here in the transition state, it is the C2 axis of symmetry that is present. It is not the sigma plane. Whereas in the disrotatory mode, in the transition state, it is the mirror plane that is maintained throughout the course of the reaction. This is now a mirror plane which is having the element of symmetry here. It is not the C2 axis in disrotation. The C2 axis is present in the conrotation. Therefore, very importantly, we need to use the C2 axis of symmetry while analyzing the conrotatory mode of reaction and the mirror plane, which is the sigma, for the disrotatory mode of reaction. After the reaction is done, in the newly formed pi and sigma bonds, both of these elements are present. Okay. What we need to consider here is the transition state. Alright, so let's see the molecular orbital of butadiene with symmetry properties with respect to the C2 axis, that is for conrotation, okay, and for cyclobutene. So what we are seeing here is the the butadiene uh, molecular orbitals and their symmetry elements, whereas we are seeing here for cyclobutene and the orbital symmetry. Okay, so now let us try to correlate the molecular orbitals of butadiene and cyclobutene, which bear the same symmetry, and these are connected by lines, okay, which are called as symmetry correlation lines. Okay, these lines that you are seeing are symmetry correlation lines. Okay, for the C2 axis, okay, for the C2 axis of symmetry or the C2 operation, let us see what happens for this particular orbital. Is it symmetric or anti-symmetric? It is anti-symmetric. So when you flip this by 180 degrees and you turn this here, then you do not get the same species. Whereas here, when you use the C2 axis and you use sigma plane, both of these are symmetric. Okay, so you are having a symmetry here with respect to the C2 axis. With respect to the C2 axis, the pi 2 is now symmetrical, whereas the pi for the cyclobutene is antisymmetric. Okay, Let's go to pi 3. In pi 3, with respect to symmetric C2 operation, this is anti-symmetric, whereas the pi 4 with respect to C2 is now symmetric. Similarly, if we see pi star, we can see with respect to C2 it is symmetric, whereas the sigma star is anti-symmetric with respect to C2. So we correlate these, the molecular orbitals of butadiene and cyclobutene, which bear the same symmetry, and we connect them by lines called the symmetry correlation lines. While carrying out the orbital symmetry correlation, one has to take care that we do not violate the non-crossing rule. Okay, that means that the orbitals of closest energy are correlated first before a correlation is made with an orbital of higher energy. So you may say that you can correlate this and this, but that is not allowed by the rule which is called as the non-crossing rule. First, you have to correlate orbitals of closest energy. Okay, so that is imperative. Now we can see here in the C2 operation with respect to the conrotation, you are now able to correlate all the symmetries without crossing the homo-lumo gap. Therefore, under thermal conditions, this reaction will be permitted. So what we can conclude, we can see that the bonding molecular orbitals of butadiene are symmetry correlated to the bonding molecular orbitals of cyclobutene. And the antibonding molecular orbitals of butadiene are symmetry correlated with the antibonding molecular orbitals of cyclobutene in the ground state for the conrotatory process. Okay, so this will be a thermally permitted situation. Now let's see the disrotation. In the case of disrotation, it is clear that the pi2 molecular orbital of butadiene is now correlating to the pi star of cyclobutene, which is now the excited state of cyclobutene. Similarly, the pi orbital of cyclobutene is correlating with pi 3 of butadiene, which is now the excited state for butadiene. In other words, the molecular orbitals of butadiene and cyclobutene are symmetry correlated only in the excited state, which implies and indicates that the disrotatory mode of reaction is allowed only under photochemical conditions. Let's now consider the hexatriene system. In the hexatriene system, we can see that the molecular orbitals of hexatriene are symmetry correlated with the molecular orbitals of cyclohexadiene in the ground state electronic configuration under the disrotatory mode. Okay, therefore, this is symmetry allowed under thermal conditions. Okay. Whereas in the conrotatory mode, you can see these are crossing the homo-lumo gap and these are symmetry correlated in the excited state. Okay. Therefore, in the case of the electrocyclic reaction of hexatriene and cyclohexadiene, the disrotatory mode is permitted in thermal conditions and is symmetry allowed, whereas the conrotatory mode is permitted under photochemical conditions because it is symmetry correlated only in the excited state. Alright, now let us go to the transition state aromaticity method to analyze electrocyclic reactions. In this particular method, the basis set of orbitals for a given system is first plotted or drawn, and the topology of the orbital interaction for either conrotatory or disrotatory modes of reaction is traced. Depending on number of electrons involved in the reaction and whether the orbital interaction topology corresponds to either a Huckel type of system or a Mobius type, we will conclude on the permissibility of the reaction, whether it is photochemically or thermally allowed. Based on the phase inversions, we will identify whether this would be a Mobius topology or a Huckel topology. When there are odd number of phase inversions, we know that this is called as a Mobius topology. Where there are even number of phase inversions, this will be termed as a Huckel topology. We will then assign the transition state. Okay, this is very important. The transition state as aromatic or anti-aromatic depending on the number of electrons present. We can assign any phases to the orbitals. It is not important to identify this basis set with any molecular orbital. Okay, for example, if we are taking hexa triene, whether we take the pi 3 or the pi 4, it is immaterial. Okay, if the transition state is aromatic, then the reaction will be thermally allowed. If the transition state is anti-aromatic, then the reaction will be photochemically allowed. Therefore, in the Huckel type of system, the aromaticity will be defined for 4n plus 2 systems, whereas it will be anti-aromatic for 4n systems, whereas the Mobius system, it will be 4n and it will be anti-aromatic for the Mobius system in the 4n plus 2 type of system. Okay, what is important is that we identify the topology. In the Mobius topology, you will have odd number of phase inversions, whereas in the Huckel type of system, you will have even number of phase inversions. Let us see what this means. In an orbit fashion, we have just taken the butadiene system. Okay, let's see for disrotatory closure. Okay, in the transition state, you can see here that there is a zero phase inversion. So this is a Huckel topology. How many electrons are there in the system? There are 4 electrons involved in the system, and this is therefore anti-aromatic by definition for the Huckel system. Okay, because this is 4 electrons. What will happen here now? This will be forbidden according to the rule. Therefore, in the disrotatory closure will be forbidden because of this particular case. Okay, under the thermal conditions. Let's look at the conrotatory closure. Okay, in the conrotatory closure, we are seeing that there is one phase inversion. Therefore, this becomes a Mobius topology, right? It cannot be a Huckel topology because this is now involving an odd number of phase inversions. How many electrons are there? We saw previously there are 4 electrons in the system. Therefore, this is according to the Mobius topology, this will now be aromatic and it will be allowed. Therefore, the conrotatory ring closure will be allowed because it possesses a Mobius aromaticity in the transition state. If we just change arbitrarily one of the orbitals, the analysis will still be valid. And this is what we had mentioned on the previous slide also. Let's consider the same system once again with a different set of orbitals. Okay, so you see here we have just arbitrarily inverted one of the systems. Alright, Let's now try to do a disrotatory closure. What are we seeing here? We are seeing that there are how many inversions? There is one inversion here, okay, and there's another inversion, okay. There are two phase inversions at this particular position, okay. So there are two phase inversions here. It's an even number. Therefore, this is a Huckel topology. We know that there are 4 electrons involved. Obviously, this will be anti-aromatic and this will be forbidden. So you can see here, even if we change the phase of any orbital, the analysis will still be valid. Let's see whether this still holds true for the Mobius topology. In the case of the Mobius topology, for the conrotatory closure, there is one inversion here, there's one inversion here, and there is one inversion here. So there are three phase inversions, so it is an odd number. Therefore, we classify this as a Mobius system. There are 4 electrons involved. According to Mobius topology systems, 4 electrons will be aromatic and therefore allowed. Okay, so the transition state according to the Mobius system for a conrotatory closure is aromatic. So according to this method, the transition state aromaticity method, the conrotatory ring closure will possess an aromatic transition state by the Mobius system and will be thermally allowed. Okay. All right, now let's go to the Woodward-Hoffmann generalized orbital symmetry rule. Okay, let's take this particular system. This is dimethyl butadiene, and let us see for conrotation, the ring closure. What are we having here? We are having how many antara interactions? We are having one antara interaction. Are we having supra interactions? No, we are not having supra interactions. We are having a pi 4 antara system. So, how many 4R components are we having? We are having one 4R component. We are having no supra component which falls under the 4Q plus 2. Therefore, the total of 4R plus 4Q plus 2 in this particular case comes out to be 1, which is an odd number. Therefore, this will be thermally allowed. So, the conrotation will be thermally allowed. Let's look at the photochemical transformation in the disrotatory mode. Here we are having 4 electron system and it is a suprafacial interaction. So both the orbitals are reacting from the same side or the same face, whereas in this particular case the two orbitals were reacting from the opposite faces. Alright, so how many antifacial interactions we have? Do we have any components with 4R for the antifacial? No, we do not have, therefore this is 0. And the 4Q plus 2 system, do we have any supra components? No, we do not have supra components that conform to the 4Q plus 2 system. Okay, therefore there are 0 components which is here, and therefore this transformation under disrotation will be permitted only in the photochemical condition. Okay, in the photochemical condition, that subsequent orbital has been chosen. Let's go to the hexatriene system. In the hexatriene system, at this point, do not bother about the stereochemistry of the reaction. Okay, we will come to the cis and trans in our next class. What gives what according to what is involved, whether it is disrotation or conrotation, and whether it is in or out system. Okay, at this moment, let us now define the generalized orbital symmetry rule for the hexatriene system. The hexatriene system contains 6 pi electrons. whereas for the reverse process it has 4 pi electrons and 2 sigma. Okay, let's look at the disrotatory mode of action, which we know is thermally permitted from our previous slides, but let us now try to see whether this also conforms to the generalized orbital symmetry rule. Okay, so this is now a suprafacial arrangement because both of these lobes are going to interact from the same face. Okay, so this is now a suprafacial arrangement. Do we have anterofacial components which conform to 4R? No, we do not have, so this is 0. Do we have 4Q plus 2 suprafacial interactions? Yes, we have one of them. So the number is odd. Therefore, according to the generalized orbital symmetry rule, this reaction is thermally allowed. Let's see whether what happens when this is excited photochemically. On photochemical excitation, okay, we are now seeing the orbital, which is the SOM, okay, the singly occupied molecular orbital. That will be the pi 4. Okay, so what interactions are we seeing here? We are seeing an anterofacial interaction in the conrotatory mode. Okay, so if this has to form a bond, this has to have a conrotation, and obviously this has to involve an anterofacial interaction. Okay, so let us see what we have. Do we have a 4R anterofacial system? No, we do not have a 4R anterofacial system because this is 6. Do we have a suprafacial interaction conforming to 4Q plus 2? No, we do not have because this is anterofacial. So there are 0 components in both the cases and this is 0. Therefore, this will be photochemically allowed. Okay, in the conrotation for the hexatriene system, it will be allowed only under the cyclization will be allowed only under the conrotation mode. It will be allowed photochemically. Okay, the reverse is true for the ring opening. If we summarize the 3 major methods that we have seen for both the cyclobutene and the cyclohexadiene systems, then we can see that all of the 3 methods will give us the same outcome. Okay, the conrotatory will be permitted for the 4N system under thermal conditions, whereas the disrotatory will be permitted under the thermal conditions for the 6 electron system. Okay, so you can satisfy yourself and see whether each of these methods, what we have summarized here, agrees to what we have studied on the previous slides. So let us conclude this particular rule that we have seen for electrocyclic reactions. When it is a 4N system, the conrotatory is allowed under thermal conditions, whereas the disrotatory is allowed under photochemical conditions. Similarly, for the 4N plus 2 system, the conrotatory is allowed under photochemical conditions, whereas the disrotatory is allowed in thermal conditions. Okay, in order to keep this in mind, you don't need to memorize everything. You just need to remember what is allowed under thermal conditions. The opposite will be true for photochemical conditions. Okay. All right, in the next class, we will see several examples of electrocyclic reactions, whether these are ring closing or ring opening, and we'll see some typical cases. We'll see some very interesting cyclizations and ring openings, and we'll see how these conform to all the rules that we have studied in this particular class. Thank you everybody. We'll see you at the class tomorrow. Goodbye.